up on Amazon a scuba mask, and from there we found the mask and the length of the goggles frame. In addition, I looked up in boatinternational.com. I found what supposedly, so first I looked up different images of different types of boats, and even though it was a little like, I don't know if it was, even though it was like old and underwater, I found that the shape was most similar to a yacht, so I looked up on Boat International the average mass and length of a yacht, and then from there I calculated torque, so we looked at the average mass and length of a yacht. So since the ship was balanced in the beginning like that, even though it was like kind of tilted, it was still balanced, so that was the net torque is 0. So the goggles are moved approximately, we predicted that it was approximately like the length of the goggles frame, which that was like seemed the most realistic, which was approximately 0.16256 meters. And also, so we used torque, so using the weight of the goggles, the torque is 0.27651 because the weight of goggles was 1.7065, which does not seem large enough to move an entire yacht weighing 5,405,914 kilograms. So it does not seem possible. So the goggles, we also use force. So we drew a free body diagram. So the goggles have their weight pointing down and then the buoyant force of the water pointing up. So we used Fukumoga for weight and then the force of buoyancy. So this is a formula that Ms. Madani was telling us. So that P is basically the density. So we found that the density of water in salt water is 1,025, and then we found, we used the density of silicon and the mass of goggles because the goggles were made of silicon. We found that on Amazon. We used the density and the mass of the goggles to calculate the volume of the goggles approximately, and then we used acceleration of gravity for G. So that's 1,025. So then we set, so basically we did an equation, we set everything equal to like Fermat. So we calculated acceleration using the two different forces. And we found the acceleration to be 5.4750 meters per second squared. From there, we did kinematics. So basically we timed the goggles falling. So from the point where we saw like them drop off of Dory to where the goggles went into the like darkness underwater, that's when we calculated the time, because from there we researched as the average height of visible light in water is 200 meters, and we approximately from like the view of the ship, it seemed like they were like halfway underneath the surface and between the darkness, so we said it was approximately, the goggles fell approximately 100 meters in the time. So we used the formula VF squared equals VI squared plus 2AD. We were trying to find VF squared. We knew that it was dropped, so it started on 0. And then acceleration we found before, and distance was 100 meters. So from there we found the final velocity 33.092 meters per second, which seems very fast for goggles to be moving, especially underwater, and with such a small mass, that seems pretty unlikely. So just to conclude, so the goggles apply such a small torque to the boat that it seems very unlikely that the entire boat would fall. It might be like a very possible, like I can't say that it's impossible, it just seems very highly unlikely. In addition, the goggles fall at a speed that seems,
What is the p-value of that?
P-value? Well, I'm sorry, I didn't do the p-value. I'll do it for you next time. And the goggles fall at a speed that seems far too fast for such a small mass underwater. Okay, so then our demo scene was Toy Story. What the heck? Yeah, you just looked. Okay, so Woody and Buzz are attempting to catch up with a moving truck while they're on its little toy car. And in order to...
and just a quick note, we're going to be addressing this in our video right now.
Yeah, but keep going. So Slinky, like the dog that has a little slinky on him, that's Slinky. So he attempts to retrieve them, but gets stretched like very, very long in the process. So the problems with this is that Slinky should have probably permanently displaced. That's our hypothesis, that he should have permanently displaced because he stretches so far, yet he goes back to normal, like right after. We're like, okay, that seems fishy. Sorry. That was by accident. Anyway, so continue. This is that's Slinky, because Slinky is stretched but appears to be far beyond his boundaries. Okay.
Oh, here's
so
the
this
scene.
I queued it up as well. So this is the actual scene.
Hold over my face.
right back to normal. Okay, so we did a demo for this, so we have our YouTube video.
Yeah, I was gonna.
Yeah. Okay, so this is our video. Oh god, it's so bad.
Cassie, have you ever watched something that actually happened? Today, my colleague Katie and I will be evaluating a scene from an animation movie, Toy Story 1. In the scene, two toys, Woody and Buzz, are attempting to catch up with a moving truck while on a toy car. In order to help their friends, the rest of their toy gang sends out the infamous Slinky in order to help retrieve them. Yet, when Slinky catches, it seems like he's drifted beyond his boundaries, yet he returns to the equilibrium position perfectly. Is this possible? Let's find out.
After stretching the slinky of radius 0.02 meters to the same displacement shown in the movie, our hypothesis was confirmed as it did not return to its original state. Rather than ending the experiment here, Tess and I went to the store and bought a slinky of radius 0.035 meters. In doing this, we would test the effect radius has on elasticity, since slinky's radius was never confirmed. After finally finding a larger radius slinky, we reconducted the experiment, only to come up with the same results. After thinking about it, it makes sense, as Hooke's law and other elasticity formulas concentrate on two main variables, neither one being radius. The first variable, x, was controlled in the experiment, while the second one, k, can change over the same material.
So how does this relate to our scene? Well, as you can see, we did not know the exact radius of the Slinky toy. Yet, we compared the radius of the small Slinky to the radius of the large Slinky, and they both displaced permanently and could not go back to their equilibrium position. So, in conclusion, we could predict that Slinky would not be able to return back to his equilibrium position. Thank you, and goodbye.
I think we busted the heck out of this one.
I busted.
Yeah.
Good one. I have a question. This is one of our slinkies. As you can see, originally it was literally like, I can't even put it back. It was literally like this, and then now it just will not go. It will just automatically pop out of.
Wow, that's ridiculous.
Thank you.
I have a question for Katie.
Yeah.
So pool party?
Yeah. Tomorrow. School night. Okay. Any questions?
Don't bring these up, bro.
All right.
No.
Good job, guys.